These are sorted by section, right? So you know what sort of to apply in what situation, right? What topics to apply where. So let's take a look at this one. Bacteria in a dish are growing according to this function. For t greater than or equal to 0, okay, pay attention, guys. For t greater than or equal to 0, where F is the weight of the bacteria, so these are things that you need to be looking at. F is the weight of the bacteria in grams, and T is the time in hours. So when we use equations, mathematical models, to represent a situation, a real-life situation, there is no guarantee that one equation is going to be true for all of eternity, right? Like a perfect example, for example, right, was, during the pandemic, right, the rate at which like the COVID was spreading kept changing, right? So like every 3 months kind of had its own equation. Sometimes every couple of weeks had its own equation. So it's always important to know how to, for what interval or for what domain is your equation valid. So this one is for t greater than or equal to 0. So first it says graph f of t for 0 to 20. So I do want to spend a little bit of time on the calculator skills. What I want you to do is go ahead and take out your calculators, please. Turn on your calculators. And when it says to graph f of t on a given interval, it's important that you take your calculator, go to Windows Zoom, under Windows Settings, change X min and max to go from 0 to 20, right? So when I graph this one, my horizontal axis is going to be the independent variable, which is the time. My vertical axis is going to be the dependent variable, which is f of t. So go ahead and change the settings and go ahead and plug that function into the calculator. Okay, so here it is. So here we go. So I'm going to go into my menu, Windows Zoom, Windows Settings, and then change this from 0 tab 20. Okay. And so when you press OK, all right, that's what you get. All right. So now you want to just transfer that here. So one way to do that is you can go either to the table. Do you guys all know how to go to the table? Yeah. The quicker way is if you do Control T and go to the table, and then so you can see here when x equals 1, this is 3.1. When x equals 2, it's 3.2, and so on, right? And then let's go down here. So like x equals 12, 3.87, and so on. Okay, and then at x, and then always put in the first point, 0, and the last point at 20, which is at 3.97. So always have the two endpoints and then put a few in between so you can draw an accurate graph like this. Okay? Now, this is all fine, but you have to, of course, label your axis. This is time in hours, and then this is weight in grams. So on a graph, you should have those labeled if you want, correct, full points. Use the graph to estimate the number of grams of bacteria present after 8 hours. So this is the same. How much is it? You can go on the table here. 3.7 grams. You can also do it using the trace feature. Do you guys know how to do it using the trace feature? Okay, so you can actually ask for the number in the trace feature. So here I'm going to press Control T again and get rid of this table. So here's what I do. Menu, trace, graph trace. And when you're in trace mode, don't just scroll through it. No. In trace mode, type in the X value, 8, enter, and it tells you here the coordinate at that point. So you can ask for it right like that. It's really cool. And then while I'm still in test mode, if I want it for 12 now, I could just put another number and I get 12. If I want 15, I could put another number. This is actually like when I'm doing this for myself, that's how I do it. And then I know other people prefer the table. Okay? All right. One is not any better than the other. Okay. So what is the limit of f of t as t approaches infinity? So we're going to do this two ways. According to the graph, right? The limit as x approaches or t approaches infinity. So if you go to the graph, if I go to Windows Zoom and Windows settings, right? And suppose I put, the max value at like 1,000. Okay? Look at how it's leveling off. Now, let me ask it how much the value is at the very edge over here. So menu, trace, graph trace. And why don't I say how much is the value at 999? Okay, it's like 4. Okay, 999 is by no means infinity, right? But okay, like it's also not like x equals 0 or 2, so it's pretty close, right? So according to the graph, the limit of f of x or f of t as t approaches infinity is equal to 4. But why don't we do it algebraically as well? Okay, the limit as t approaches infinity of that cute little function okay, well, what is that? Let's see. This is the limit as t approaches infinity of 4 over 1 plus 0.35. And why don't I write that as e to the, I'm sorry, that's not what I meant. E to the negative 0.2t, I want to write it as 1 over e to the 0.2t. Right? So now I can visualize it better. I can see it better. So now when t is infinity, or when t is infinitely large, e to the infinitely large exponent is infinity. 1 over infinity will be what? 1 over 0. So this will be 0. That means this whole thing will be 4 over 1, which is 4. Do you see that? Okay, interpret your results. What does this mean? 1 over an infinitely large number is about 0. 0 times this is 0, plus 1, 1. Okay. So, interpret your results. So what was this? Bacteria in a dish are growing according to this function. And then this is the limit as t approaches infinity. So can somebody raise your hand and tell me, what does this mean? That the limit as t approaches infinity is 4 of this. Yeah. Huh? Well, we don't know anything about the dish. This is about the bacteria. Huh? Right. So it doesn't matter how much time passes. Okay, the maximum amount of bacteria in this dish will always be 4. Okay? So the maximum amount of bacteria in the dish will be 4 what? 4 bacteria? 4 grams. Okay? All right. So, okay, we've seen this one, right? We've seen this problem from the homework, remember? Okay, so this is the mass of an object with velocity v. Okay, we know m naught is the mass of the object at rest. So like this, whatever mass this has, that's m naught. But if this was flying at the speed of light, it would have different mass. That's what this says, yeah. So what is the mass of the object? I'm sorry. What is the limit of m as v approaches c from the negative side? So let's go ahead and do that. So the limit as v approaches c from the negative side of this thing. Okay. Okay. So c from the negative side, right? That means v approaches c from the negative side. That means this is just under c. So let's say c was 3. This would be like 2.99999, You see that? Okay. So now, so this will be 1 minus a very small number. Okay? And what's 1 minus a very small number?
1.
1. And then m naught over that 1.
M naught, just M naught.
No. Sorry. As v approaches c, how much is this?
1.
Almost 1, because these are the same, right? This is like 2.999, and this is like 3. Sorry. I was thinking about something else. So v over c, so what if these are almost the same? This is almost 1. It's like 0.9999999 or something. 1 minus that is about 0. And then m naught over that will be positive infinity.
I have a question.
Yeah.
How do you know that like the V and the C are like similar? Like,
Because
you just know that.
Okay. So as v approaches c, okay, the mass will get infinitely large. Okay, Matt determined that the voltage in an electrical outlet in his home is modeled by this function. What is the significance of this? Okay, so this is the voltage. So here we're being asked, what is the significance of the limit as t approaches infinity of v of t, right? So if v of t is the voltage, what this is saying, this quantity is, what will be the value of the voltage? How much will the voltage be after a very long period of time, right? So now, it really doesn't make sense to say after an infinitely long amount of time. How much is an infinitely long amount of time? Like as much as it took for the dinosaurs to be extinct, right? Okay, is it like 3 million years? Or is it 50 million years? Or is it 2 seconds? Well, okay, for each situation, an infinitely long amount of time means something different. Do you see what I mean? Like in the case of a voltage, an infinitely long time could just be like a fraction of a second, right? Because that's how much it takes like for the voltage to like load up or something. Now, you wouldn't need to know all that, right? But what you could say, instead of saying an infinitely long amount of time, you would just say, so this represents the voltage in the outlet after a long period of time. Okay. All right. So when you're like, let's say you're talking about like how long it takes for like dough to rise, right? Okay. Nobody's going to leave the dough out for like 3 million years and see like how much does it rise. Okay. So like an infinite amount of time over there will be like a couple of hours. Do you see what I mean? So like refrain from, using these like, like it's almost like a hyperbole. You know what I mean? Okay. So what does this exist? Why or why not? So let's see if it does exist. So the limit as t approaches infinity of this function now, okay, this is the limit as t approaches infinity of this function. What is this function? 140, that's the amplitude, sine 120 pi t. How we find period, right? 2 pi over b. So this is like some function, some like sinusoidal function. Okay, so if this is a sine function, do we know what's happening to it at infinity? No. So this is just dne. Okay? It does not exist. It's dne because it's a sinusoidal function, and we don't know, sinusoidal functions that oscillate are infinite at dne because we don't know where it will end up.
And
So
the
then,
opposite
would it be
is-
like positive then? And negative?
It's not infinity, it's just
Oh.
DNE,
Oh, okay.
because we don't know anything about it.
So we know it's oscillating because of the one.
Because it's a sine function. It's just a
So-
regular old sine function. Okay, so
Any
the,
trig function would be oscillating.
I mean,
No, it's like
Mm.
tangent cosine.
Yeah, but also
Tangent is not
tangent
oscillating.
has effects, right?
huh?
No, it's
Tangent.
Right, tangent has that, but even like tangent at infinity will be DNE. Okay? Yeah. Okay, periodic functions, yeah. Okay, and so, so the amplitude is 140. All we know is that infinity, it's oscillating somewhere between positive and negative 140. Okay, let's move on to section 2. A pool contains 75,000 liters of pure water. A mixture that contains 0.3 grams of chlorine per liter is pumped into the pool at a rate of 75 liters per minute. Okay? The concentration C of chlorine in grams per liter T minutes later is given by this. So do you guys see, like, you start out with fresh water and now you're pumping in water that has, this much concentration. So the water that's being pumped in has 0.3 grams of chlorine per liter. Eventually, the entire chlorine content of the pool will change, yes? And that chlorine content or concentration is changing according to this. So find the limit as t approaches infinity and interpret your results. So the limit as t approaches infinity of 0.3 t over 1,000 plus t. Now, this is a rational function which we need to find as t approaches infinity. So take the leading term, take the leading term. Do you see how the situation does not matter? And in section 2, we learned if you have a polynomial function and you're evaluating the limit at infinity, take the leading term, take the leading term. Now you've got a pool and you've got chlorine and you've got this. But the way in which to find the limit at infinity does not change, right? Because the math cannot change. So this will be how much? 0.3. And it's actually grams per liter, right? Because that's the unit over there. So to interpret your results, as, did you find her?
Yeah.
Oh, okay, okay. As, so as the mixture is pumped into the pool, okay, here guys. Okay, the concentration will never exceed 0.3 grams per liter. So even if you are pumping this for 3 million years, the concentration is never going to exceed 0.3 grams per liter, okay? The concentration will never exceed 0.3 grams per liter. Okay? You can also say like the maximum the concentration will reach is 0.3 grams per liter. They all mean, like, they all say the same thing. Okay. So Flint bought a new motorcycle for $24,000. Can you buy a motorcycle for $24,000? Is that reasonable? Not anymore, probably. Well, maybe it's more like a scooter, a moped.
I don't know. How much
A moped.
How much are motors?
24. I have no idea how. I mean, it's
I'm assuming.
surely not a Harley Davidson. Come on, it's like, Okay, no, we're not looking it up now. Let's do this. Suppose the value of his motorcycle in thousands of dollars after 2 years can be represented by this equation. Is this an exponential or a linear function? Is this growth or decay? Decay, because this is less than 1. Okay, it's decaying slowly because it's very close to 1, but still. All right? So, okay, very quick. You know what? No, later. Because we need to be here. Okay, so, so complete the table, round answers to the nearest tenth. You all know how to do this, yeah? Plug it into the function, t equals 1, t equals 5, blah, blah, blah. So the values you get are these. So, okay, so we looked at the problem, We established that it's exponential. We established that it's decaying. And so now with that piece of information, we can, reason out whether the answers we're getting here make sense. And if the numbers are going down, then yes, my answers are reasonable and they make sense, right? So the point of the stuff that we're doing today is to be able to make you like this well-rounded, like woke math student, right? Where you can just like look at these problems and you just have like this, sort of like rounded understanding of what's going on. So again, you're seeing a pattern here. What is the limit as t approaches infinity? So we predict, right? If this is an exponential decay function, eventually it will decay down to 0, right? And then if you look at the function, does it? Okay, 0.98 is a fraction less than 1, right? To the power of t, if t is infinity, you're still going to have 1 over infinity, so it'll be 0,
And we know
right?
it can't be negative just because it's in dollars.
Well, no, wouldn't it only be able to decay to 24 because when t is 0, then 0.98 would be 1, and then it would be 24.
No, so 0.98 is a fraction. Let's say it's like, 1 over, 10 or something, right? So this, to the power of t, when t is infinitely large, this will be about 0. Okay? So there is a point where you're actually like losing. So it's,
because we aren't doing
right.
t to the 0, we're doing t
Right.
is infinity.
So now, take a look. Hang on. So now take a look. The limit as t approaches infinity is 0. Will this ever really reach 0? No, because there is an asymptote there. And that's exactly where this limit idea comes from. The value approaches 0, right? Limit never says the value will be 0. It says it approaches 0. So no matter how worthless the motorcycle is, you'll still be able to sell it for something, right? So there's, okay, come on. I'm not looking for opinions here. Like, we're not discussing this, but do you see what I mean? Like, you can sell it for scraps, you can sell it for something, but like, do you see how the math, like, totally goes along with the actual facts of it, right? It will never just be completely worthless, okay? Yeah.
Look, I understand that, but then if they didn't give us like dollars and like it was just like the numbers itself, then like could we assume it's like negative infinity then instead of going to 0?
Well, okay, so now when you go into the word problems, each of these represent a real life situation. So you have to decide in that real life situation what is a proper domain. Okay, if this is modeling like the cost, does it make sense that you're right? Because t is time. You know what I mean? So does it make sense that it's negative? And it's also an exponential function. There is a horizontal asymptote. We know exactly how it looks. You know what I mean? Like, there is no way this will be negative. Okay, we know this because we've done chapter 3. Okay, so the cost C of producing a certain small engine part in dollars is given by the equation this. Okay, so this is cost. P is the number of parts produced. Okay, find the cost of producing 100 parts. And I know this is like a total no-brainer, but the point of me writing this is so you guys know notation. So what you would do is C of 100 is 5,000. And before you ask, do we have to write C of 100? I'm really trying to make you like elegant and dignified math students here. So I'd rather not even entertain that question. Okay, moving along. On Tuesday, the company, I don't know why it's a Tuesday. I don't know, I made these years ago. I wonder why I made it a Tuesday. On Tuesday, the company produced $21,000 worth of parts. How many parts did the company produce? So this is going to be 9,000 equal to 3,000. And this is totally a no calculator problem. Okay? I don't know. Because The answer is 900. That's why. I don't know what I did. I got messed up. It's 21. Okay. So when you divide, when you subtract this, what do you get? 800? 18,000. Oh my gosh. So P is 900 parts. Okay? Okay. The average cost per part is found by dividing the cost per number of parts. Find the limit of this as P approaches 15,000. Okay, so let's do that. The limit as P approaches 15,000 of, what was C of P? It was 3,000 plus 20P over P. Okay, how would we do this? Just plug it in, right? And again, this is like one of these no-brainer-ish type things, but why did I put it in here? Because until now we were doing infinity, T approaches infinity, and we're taking the highest degree over the highest degree. And now you look at 15,000, this is not infinity. This is still a very finite number. It could be like 3, right? 15,000 is more like 3 in the math world than it is like infinity. So you just plug it in, and what do you get? 20.20, yeah.
Why don't you have to write for like right before you plug it in? Why don't you write limit as P?
I did.
Oh,
Oh, here, because you already plugged it in. Once you plug it in, it's no longer a limit, it's the actual value. Okay? All right, so here, okay, so remember this is like money, so it has to go to 2 decimal places. Okay, so let's go to this next one. Oh wait, did I not put, oh, I didn't put the other problem over here. It's okay. All right, I had a couple more problems, but I took them out because, okay. I wanted to do this one because it's a little bit different, right? We've been doing rate problems, and all the rate problems we've been doing are like speed and velocity. This is a little bit different, okay? All right, so suppose the length x of each side of a square shown is, okay, by the way, this problem too is like straight out of calculus. This is why I've put this one in here. Okay. Suppose the length x of each side of a square shown is changing. So suppose like, somebody is like dragging this, back and forth or whatever, and the length x is changing. Find the average rate of change of the area, A of x, as x changes from 5.4 to 5.6. So if you want average rate of change, it's the final value minus the initial value divided by 2. Divided by the difference, right? So if you want the average rate of change, what this is actually the slope of that lovely secant line, okay, of A of x as x changes from 5.4 to 5.6. So this is x1 and this is x2. So what we want is A average. Okay. Okay. So this is going to be, I'm sorry, what we want is the average rate of change of the area, right? So what is this going to be? What is the area when x is 5.6? It's 5.6 squared minus 5.4 squared all over 5.6 minus 5.4. Okay, so this is 2.2 over 0.2. Okay. So this is going to be 11. Okay, now let's talk about the units. So this is the rate of change of the area. the rate of change of the area. So this is 5.6 squared, okay, in inches. So what is the unit for this? Inches squared. And what is the unit of the bottom? Inches. So what's the rate? What's the formula? What's the unit for the rate then? Inches squared per inch. Okay? Because this is the rate of change of the area. So what we're saying is the area is changing at a rate of 11 square inches per inch. Okay? So it's inches square per inch. You can't cancel those. You know why you can't cancel those? Because what is a square inch? That's a square inch. What is 1 inch? It's that. These two are different quantities. That like they're completely different things. They're not the same thing for you to be able to cancel. Okay? So the unit is going to be inches squared per inch. Okay. So go ahead and do this one. The expression for the instantaneous rate of change of the area. So what is A of x? It's x squared. So the instantaneous rate of change is x plus h squared minus x squared over h. So this is x squared plus 2xh plus h squared minus x squared all over h. Oh, yes. So this is the limit. H approaches 0. H, so these go away, times 2x plus h all over h. So finally, this will be 2x. Yeah, but you don't have to write the units for this one because it's not like an actual quantity. The next one, however, find the instantaneous rate of change of the area at the moment x equals 5 inches. When x equals 5 inches, the rate is 2 times 5, 10. So it's 10 square inches per inch. So at the time that, the square is 5 by 5, the rate of the area is changing at 10 square inches per inch. Okay? All right. So that much for that.